Hello everybody. I hope that you've all had a good lunch and you're ready to get started with some routing protocols. So my name is Manas and I have my colleague here, Sumit, here with me. And we will be taking you through the session today. So first of all, NAT, a practical approach. Now NAT, according to me, is a technology that is oft underestimated. It is something that ends up coming and biting us at times when we didn't really expect it. It's something that we see a lot of cases on because we are troubleshooting engineers and we see customer scenarios on a day-to-day basis. And we think understanding NAT at a basic level, typical scenarios, things that you need to do, so on and so forth, would really help us, work with our day-to-day setup, better, because NAT is something that's deployed extensively across different scenarios across all of our, networks. So let's dive straight into it. So over today's session, we'll spend a little bit of time initially just running through why do we need NAT at all, what are the different kinds of NAT that you can do on a Cisco router, what are some case studies or scenarios where you see NAT implemented, and some best practices. What are some of the things you should keep in mind when you're working with NAT? What are some of the things that can go wrong, and so on and so forth. Now, let me just add right here, over the course of the session, if you have any questions, like Shiv already mentioned, feel free to use the question and answer section and type in the questions. If that's something that's directly connected to what we are talking right now, and there's something we can answer right away, we'll go ahead and do that. Otherwise, we'll try and come back to as many as we can towards the end of the session. All right? So let's get started then. The first question, why do we need NAT? What are some of the advantages of using NAT? And some of this is generic and most of you might know this, but let's just run through it really quickly, right? The first thing that NAT allows us to do is it gives us some security. It hides the user's identity. So when I'm NATing my IP to another IP, as far as the public world or the outside world is concerned, they see me with a different name or a different address. So it gives me security. Secondly, and this reality is even more true to us in India, IPv4 is running out pretty fast, right? If we were to start assigning IPv4 addresses to every device out there, these days every phone, mobile phone, tablet, laptop, PC, we wouldn't last very long, would we? So NAT is something that's been in place for a while to help us to be able to reference many different devices and machines with lesser number of IPs, sometimes one for thousands of machines altogether. Okay, let's look at what are some of the different flavors of NAT, right? And at a high level, you can split up NAT to static NAT and dynamic NAT. Let's step through one step lower than that, right? Now, static NAT can further be looked at as 1:1 NAT, where you're saying one inside IP would get mapped to one outside IP, right? Where you want to 1:1 NATing. What is the second part of static NAT say? It says port address translation, port forwarding. That's the phrase that people normally use when they're referring to this type of static NAT. What you're saying is you don't want to open up an entire IP to an entire IP and use up all 65, 30, 36 ports, but you want to use specific port numbers. So that will allow you to do more things as we'll look at in the scenarios that are coming up. The second high-level thing, like I said, is dynamic NAT. Dynamic, as the name suggests, means that the entry doesn't exist automatically as traffic comes in. It dynamically gets created. Now, dynamic NAT can again be 1:1, which means that if you have 10 IPs getting mapped to 10 IPs, we can have them dynamically get allotted to different IPs. Now, another flavor of NAT is dynamic NAT with overload. This comes into the picture when you have a large number of users and a limited number of IP addresses. And all of this we will cover in the scenarios that are coming up, right? One of the things that we'll try and do is give you as much of commands as possible and show you these scenarios or these situations and configurations on actual Cisco devices, okay? So we're going to step into some common scenarios now. Let me give you the first one. Okay. Now, let's say this is a setup. We have some internal users. There's a router that's doing NAT. There's a NAT inside and an outside, and the cloud signifies the outside world. Let's take a closer look at it. So let us assume that there are 10 users that want to access the internet. hope I'm not speaking too fast. Somebody was talking about delay over the audio, so I'm going to speak slower. Maybe that'll help, the audio catch up. So we have, let's say there are 10 users to accessing the internet, and there are 10 public IPs, right? Now, what kind of NAT can be configured to make sure that each user gets an IP address and is able to go out? So because of the scenario that you're in, what I would say is we can use dynamic NAT because it's 10 users and 10 IPs. So the configuration for that would be an IP NAT inside source list 100, where 100 is referring to the users who are on the inside, and a pool with a NAT pool. This NAT pool here is going to reference the 10 public IPs. So as a user comes in, hits the IP NAT inside, gets routed out, hits the IP NAT inside, would get assigned an IP address. So each new user that comes in would get a new public IP address as they get NATed. Okay? Now, before we continue, what I'd like to do is show you my lab. We have a lab that we'll be using throughout this entire session. It'll be useful for us to take a look at that lab itself, so we all know what are the devices and how they're connected. Okay? So give me a second, I'm just bringing that up. Okay. I'm hoping that you can see this lab topology that I have here, right? And we'll reference some of it. Most of the NATing that we'll do will be on the router right in the middle, which is labeled as the WAN router, on which we will configure the NATing to NAT the internal users towards the outside world, right? So we have some machines on the inside, and we have a server, we have devices, and that's going out. Okay? I'm hoping that part is clear. Now, let me just quickly hop onto the WAN router and show you something. Okay?
डिटेल पाठवले रे अमोल मला नाही
त्याला सांगितलं मटेरियल जे आहे ना तुम्ही फक्त अभिनंदन टाकता बाकी कुठलेही प्रोडक्ट आम्ही कोणाचे आहेत तुमच्याकडे दिलं नसेल तर मग मी
हे ते डिटेल म्हटलं
बरोबर आहे सॉफ्ट कॉपी मध्ये एक्झॅक्ट मला
Yep. Okay. I'd request you to not unmute yourself so that we can, continue without further interruption. All right. So I was going to show you the WAN router, right? So we have the interfaces here. So if we go back to that diagram for a second, you can see that the inside interface here is the one that we have with the private IP address, which is Ethernet 00, and we have two ISPs that are connected to this router, one in the 6.6 subnet and one in the 7.7 subnet, right? So to enable NATing, the two things that we always need, and like we did see in that basic setup as well, is to mark the inside interfaces and the outside interfaces, right? So I'd go to Ethernet 0/0, mark that as IP NAT inside, right? And similarly, I'll go to Ethernet 0.1 and 0.2 and mark them as IP NAT outside. Let me quickly do that as well. Right, so the configuration that we did in that particular example was simply to allow an entire pool. So let us say that I have an IP NAT pool which I've configured in this range, the 6.6.50.6.5, because that's the IP address of that first provider. So I say NAT underscore pool right? So it asks you for a start IP and an end IP. So let's say it starts from 1 through 10. And then Let's say that's a /25. All right, so now we have the NAT pool. The configuration to complete it would be the last part, IP NAT inside, source. We did not create the access list yet. Let's do that. So what was the inside IP address? Let's take a look at it. The inside IP was 10.1.123. So as I do this, you want to keep an eye on making sure that you check these little things. When you're troubleshooting, when you're setting networks up, you want to make sure, okay, I want to make sure that I specify everything as specifically as possible, right? So a specific access list in this case would be, say, access list 100, permitting 10.1.123.0.000.255. Oops, typo there. 255 going anywhere. I missed an IP. And then I would put in the NAT statement, which is IP NAT inside source list 100 pool NAT underscore pool, right? So this would allow users in the range of this access list, if they come in and hit the IP NAT inside interface, which is Ethernet 00, and they're trying to go out the IP NAT outside interface, they would get NATed to the IP addresses specified in the pool, right, which we just did. Now, just one thing I wanted to highlight before we continue. Look at the order in which this was done. And that's also, I mean, it's a little thing, but it's something you want to be aware of and make sure that you do it in that order, right? Access list, pool, or one of them first, and then you do the NAT statement, right? Okay, now I'm going to continue back to my slide deck, and I'll go to the next scenario, right? So this was a very basic scenario where we were trying to get 10 users to go out, and you have 10 IPs that you can use. Scenario 2. Now this is a little more, configuration based, more what you would see in a real world scenario. It's not 10 users anymore. As you can see, this company is expanded, and those 10 users have now grown to 500 users. Now all of these 500 users need to be able to go out to the internet. How many public IPs did they have? We already talked about that. They have only 10 public IPs, right? Now we need to configure it such that all of these 500 are able to access the outside internet. The IP NAT inside remains the same, the IP NAT outside remains the same, but now we use a keyword at the end of it called overload. IP NAT inside source list 100 pool NAT pool overload, right? Or there's another example of that, which is IP NAT inside source list 100 interface fast Ethernet 4 overload. Now the difference between the two is simply the fact that a NAT pool you would end up using when you're using a range of IP addresses, or you're trying to use a single IP but it's not the IP on the outside interface of your router. But what if you're a small office, right? You have a single IP that your ISP has assigned you, and you need to do all of your configuration based on that. Or even another scenario, what if you're using something that gives you a dynamic IP that keeps changing? Your DSL modem sometimes does not give you the same IP each time you connect. In which case, you would need to specify the interface and do an overload so that the NAT continues to work irrespective of the IP address that you have at that given instance of time. Okay, so as far as the config is concerned, there's not that much for me to add, but I'll just simply add there as well. So a NAT statement would not be, where's our NAT statement? Yeah, it won't be simply that. In fact, it would be IP NAT inside, the same pool, everything else remains the same, but I use overload at the end of it, right? What overload does is that it makes it possible for those 500 users to get out by assigning port numbers from that outside NAT pool so that each user or each flow that is going through the router that needs to get NATed becomes unique. Okay, now let us continue with the scenarios again. Scenario 3. What's happening here? This is a little different. We have the internal users, like we talked, and there's a server. How do things change when it's a server? When it's a server, then we're not talking about internal users going out anymore, are we? We're talking about somebody from the outside coming in. So, just like a website that you might be hosting at your end, right? So if you're hosting a website, then a public user from the other side is coming in, hitting the NAT outside, through the NAT inside, comes in and reaches that web server which is on the inside. Now the configuration wouldn't work with the IP NAT inside. The dynamic NAT wouldn't work. And the reason for that is because dynamic NAT is one-sided. It hits in when traffic goes from the inside to the outside for the statement that we wrote earlier, inside source list overload. So let's take a look at how it would work in this particular scenario, right? So the configuration with a single server and a single public IP, right? We have a single public IP as well in this case. So if the public IP that you have is 100, 100, 100, 100, the public user with this statement in place would come and hit IPNAT outside. The IP address that he would be trying to reach, your server's IP, is 100, 100, 100, 100. That would then get translated to 192.168.1.100, the destination that is, and then the packet would reach the server. The server would respond and the connection is established. Okay, I'm hoping that part is clear. Let me just quickly show you that as well. So as you can see, I'm removing the older NAT config as I show you a new config. That's just to make sure that our config looks clean as we continue working on this, right? So in this case, it is basically IPNAT inside, source static, and you want to specify a static IP address in the local subnet. Now in the slide deck that I had, I used a 192.168, but our case in this case is 10.1.123. So I'm going to use something in that subnet to demonstrate it here. So it's IPNAT inside, source, static, 10.1.123. Let's say 10 needs to get natted to 100.100.100.100. Okay. Now, when somebody tries to hit 100.100.100.100, they would then get natted. The destination would get natted to this IP, and it will continue to flow. Okay. All right. That is this scenario. Now let's take it a little bit further. We are extending on the scenario 3 in this particular case. What happened here? We don't have one server, we have two servers now, and this is a real normal scenario, right? It's not that one server is going to be handling all of the different kinds of accessible traffic that we need from the outside. You might have a different email server, you might have a web server, you might have other different servers that you have on your network that your public users need to be able to access. What's the challenge here? We have multiple servers, but a single public IP. So can we do it with the same kind of NAT that we did earlier? No. Why? Because if you were to map the web server's IP to one public IP, what will happen to the email server, right? So in this case, we don't do a one-to-one static NAT. We still need static NAT because it needs to initiate from the outside, but we will use a port forwarding. We'll specify a certain port. So the emails come in on TCP port 25. The web server is TCP port 80. So let's take a look at the config that we'll put in there, right? So IPNAT inside source static TCP 192.168.1.100. So we are taking the web server here to be 1.100, just like in the previous case. But we just take port 80 here, not the entire IP, because we specify TCP. It allows you to specify the port and the outside IP as well, and port 80. What about 25? The same thing, IPNAT inside source static TCP 1.200 in this case, because 1.200 is the IP address of your email server, with port 25, which is your email port, outside IP, and port 25. So what you've achieved here basically is that with a single public IP of 100, 100, 100, 100, we were able to access two different inside IPs on different port numbers, of course. Now, it might happen in a real world scenario that you have two different servers on the inside which need to be accessed on port 80. So what you can do is on the outside, if you use two different port numbers, you can still reference port 80 on the inside, and you would be able to set that up. Okay. Okay, I was just catching my breath because I've been talking non-stop. All right, let's take a look at this. Different type of NAT addresses. So if you've ever done show IPNAT translation on a Cisco router, right? And let me just bring that up. I wouldn't have anything active right now, and we will get into some of the active translations soon. But you see these things here: inside global, inside local, outside global. It's very important that you understand exactly what these mean, especially when you start stepping into more advanced NAT scenarios, because in those scenarios, this basic understanding becomes crucial. So I'm going to take a minute or two to just go over the different NAT IP addresses that we talk about, right? So we take the typical scenario that we just mentioned. In this case, the server is outside though, where, just like an internal user trying to access the internet. So you have a list 101 for the internal users, fast Ethernet 4, it's a simple one IP user, overload, so it's going out. All of these users go out with the same IP to the server on the outside. Now, I talked about the 4 IP addresses: inside local, inside global, and outside global. Okay, Now, the key words here, there are two words that you see used multiple times. The inside, outside, and also local and global. So let's talk about what these are referring to, right? So if you want to look at the router, if you look at the router and draw a line right in the middle, I like to say that everything on the left is inside and everything on the right is outside, right? Now, the view of the IP address from the devices on the left, the internal users and so on, is called the inside local. The view of there, as far as the outside world is concerned, is the inside view of the global, which is inside global. So when the traffic flows from the internal user, gets NATed on the router, and is about to go out, the IP address that it gets NATed to is the inside global, right? Now the IP address you're trying to reach, on the other hand, which is from the outside world's perspective, the outside local is the server's IP, 100, 100, 100, 100, right? And we are not doing anything to that IP address. That doesn't change. So the outside global remains the same, 100, 100, 100, 100. I'm hoping this is clear to you, and it's important that it is. So I'm going to take a packet and show you exactly what happens when it goes out, right? So let's imagine that this is a packet. I know it's not a very good packet, but it's a packet there. You have a source which is inside local. What is the source IP of this packet? 192.168.1.1. The destination of this packet is the outside local, correct? Because that's the way the outside world is looking at the local IP. So that's 100.100.100.100. That's what it's trying to get to. So this packet goes from the PC up to the router. It hits the router, it hits IP NAT inside, and then what happens then? It gets routed out. So as it's getting routed out, you saw it go route out, you saw that the source changed. What happened to the source? The source that was IL, or inside local, changed to OL, or outside local. Why is that? Because of this NAT statement, which is IP NAT inside source, which said when traffic hits the inside interface, change the source to fast Ethernet 4's IP. So in this case, fast Ethernet 4's IP is 1.1.1.1. So the IP address of 192.168.1.1 got translated to 1.1.1.1, while the outside IP remains the same, right? And I'm hoping this flow is clear to you. Again, I repeat it because, like I said, it's one of those basic crucial things that one needs to understand. Now, there's one more crucial component, again, basics of NAT, which we need to discuss. I don't have a slide for it, but I remember it when we were talking about this. When packets come and hit the inside interface, IP NAT inside. So let's go back to the scenario where the packet is coming from here and hitting IP NAT inside. So on a Cisco router, when traffic hits IP NAT inside, the first thing that it does is that it looks for the routing. It says, where is this packet trying to go? Oh, this is the destination IP. Let me route the packet out the outside interface. If it hits an IP NAT outside, then NATing happens. Okay, so packet comes, hits inside, does routing, then NATing. Why am I telling you all this? Because if you're looking at it backwards, let's say traffic is coming from some outside device, say that server is trying to contact you. It comes and hits IP NAT outside. It does not route the packet. It first NATs the packet. So looks at that packet and say, can I NAT it back to some other IP on the inside? Do I have an existing NAT entry that I can use to send traffic back? Even in this scenario, right? If the inside user was trying to access his website, let's say that's a website. So the connection would go from here, hit the inside, get routed out the outside, source gets NATed like we said. Now the server has got a source IP of 100.100.100.100, the source IP of the server responding back, right? Now the destination IP of the server will be the inside global, right? Will be 1.1.1.1. But when when it tries to hit this outside interface, what it will do before it tries to route it anywhere is check for NATing. So it checks the NATing and says, oh, I do have an entry. 1.1.1.1 is supposed to be 192.168.1.1. So it NATs it back. Then the routing happens to the translated IP of 192.168.1.1. So the whole point of discussing this, besides understanding the inside locals and globals, is to talk about the order of operation of NAT. So remember this as a general rule of thumb. Hits an inside interface, first route, then NAT. Hits an outside interface, first NAT, then route. That's pretty much what you need to remember from this particular section. Okay. Now we're going to start looking at some special scenarios. Right? I'm going to say I have Sumit take over. I need a break and have a sip of water. Sumit? Thanks, Manas.
Yeah, hi guys, I'm Sumit and I will be taking over for some time. So we will now discuss about special scenarios that we have. So those are the basic scenarios that Manas covered, which we see most of the time in deployments. And so we do not get a lot of cases for them, although they are the most used because they are sort of simple, right? So these are special scenarios where if you do not have a proper understanding of NAT, you do some misconfiguration and you run into issues. The first one is if you have multiple ISPs in place. So what if I get two links from different ISPs and I want to use both the links at the same time, right? So my users can use the NAT out, the ISP1 link to go out, or they can use NAT the other ISP link to go out. So right now I'll talk about the very basic scenario where I just need to get double bandwidth, right? Means one ISP gives me 10 Mbps, the other one gives me 10 Mbps. I want my users to get into the router, get load balance, and some traffic goes to the first ISP, the other one goes to the other ISP. I do not care which one goes where. I just want it to work by using the link. Right? So how do we configure that? Right? So the configuration for that is a little different than what we saw for the basic NAT configuration, where we were using an access list to match the traffic. In this case, we will use a route map to match the traffic, which will have an additional statement, which is this match interface Ethernet 0/1 and match interface Ethernet 0/2. So when the traffic comes from inside, as Manas has already covered, into out, first thing that we do is routing. So based on CEF, if we are doing equal cost load balancing and just doing the default route, the router will choose either to send the traffic on E0/1 or it will send traffic on E0/2. So that is the routing part. When that part is done and packet is ready to be sent out, router will also check the NAT configuration which is in place, right? So here it sees NAT configuration is matching this particular route map, which is also matching the interface. So if the packet is going outside on Ethernet 0/1 and it matches the access list 1 and it is matching the interface, it will get NATed to the Ethernet 0/1's IP and go out. Similarly, if it goes to the other one, it will get NATed there and will go out, right? So we will also discuss some trips, and we'll see how, if we miss some of these things, how things might break for us. There's another very interesting scenario where we have a server which is, so there are multiple uses. So what I'm going to cover right now is IPNAT outside. So there are multiple test cases where IPNAT outside is used. It is one of them, right? So the basic idea is if someone from outside comes in, his IP should change, right? So right now we were seeing when we are going in to out, our source IP changes. In this case, it will be opposite. When we are going in to out, our destination IP changes, right? So for that, so the test scenario that we're using is we have this one particular server which is only accessible from the inside users. Right? The policy on the server says that it should only be accessible from some set of IP addresses which are local to us. Now we get additional company, we acquire that, or we get a partner, or we come up with some of intranet where this particular user, some outside user, also need to access our server. Now in the traditional way, if he tries to access us, his IP will be a public IP address which might be dropped by our server, right? So we have to change his IP address to a private IP. So the configuration for this is just the opposite of what we've been doing. Instead of using IPNAT inside, we will do IPNAT outside. Okay, so IPNAT outside, source static. So we are using static configuration. If we want, we can use dynamic also. We can use list. Source static, the IP address that the server had, this is the outside global IP address, and this is the outside local IP address. So what IP it will have when it gets inside. Alright, so this is the way to remember it. IPNAT outside, source static. That means when I'm coming from out, this is the out of IPNAT outside, okay? When I'm coming from out, change my source. Alright, so when this public server comes from out, change his source from 100 to 192, right? So that means for the reverse traffic, things will be switched off. switched in a different direction, right? So that means when you go from in to out, it will change the destination because it was changing the source from out to in. Alright, so I'll just give you a couple of seconds on this. IPNAT inside source, change my IPNAT outside source, change my source when I'm coming from out to in. Similarly, when we have IPNAT inside source, that also means the same thing. IPNAT inside source, change my source when I'm going from in to out, right? And for reverse from out to in traffic. Now, this has been covered. Now we will go to common issues that we see with misconfiguration in NAT, right? All right. So we'll start with the first configuration that I said, and this is a very common deployment that we are having these days, where we get two internet connections on the router. So as I discussed in the last slide, the correct way to do that is having also a match interface. So we can see that someone tried to configure this router, configure it IPNAT inside source list, and had two interfaces with an IP to be overloaded, right? So the problem with this configuration is when the packet comes from in to out, right? The packet comes in, hits the router, it does the routing, and routing and NATing are independent. They're not dependent on each other. They are independent actions that are taken by the router. So the routing decides the traffic has to go out from the first link or the second link. So based on the load balancing, it can choose either. Then which NAT statement it can take. So it can take either one of them. So if the traffic goes out through Ethernet 0/1 and the NAT that is hit is the first one, interface Ethernet 0/1 overload, things will be good. We won't even see a problem, right? But the problem will come if the packet comes in, goes out through the other interface, Ethernet 0/2, but gets NATed to the Ethernet 0/1's IP, right? The statement here, interface overload, does not tell the router to match an outgoing interface. It does not tell the router to route the traffic in a particular way. It just tells the router the NAT the traffic to this IP address. For all we care, this IP address could have been a loopback interface, which is not an exit interface. Right, so that's why we should not get confused that because they're doing interface overload, it will only be triggered when a traffic is going out of that interface, right? So that is independent of our routing decision. So to fix this, as I showed in the last slides, we should have, instead of matching a list, we should match a route map, which matches the outside interface and which also matches the access list of the traffic that we're trying to send. And this is one very, very interesting scenario where we have one server. So earlier in this slide, we didn't care about where we go out from. We just want the traffic to go out and just need our load balancing things to be covered up. In the other scenario, we have a different thing where we have a server which we are hosting, and we want it to be hosted on two ISPs because it's a server. It is critical for us. We are a small business unit, but we have taken two internet connections from two different ISPs, and we want those ISPs to be available in case of a failover. If one of the ISPs goes down, we are available from the second ISP. So our server is not black hole. So if we configure a statement like this, which I did here, IPNAT inside source static, we are statically NATing the server to different IP addresses. We'll see what the problem is that we can run into, right? So because this is a server, I will talk about the traffic being initiated from outside, right? Server is the recipient. Traffic starts from outside in the cloud, comes back in, and now we'll see what is the problem we might run into. Traffic comes in, hits the router. So let us assume the outside IP here is 100, 100, 100, 100. Hits the router on 100, 100, 100, gets NATed to 192.168.1.100, reaches the server. No problem in that. Another client is trying to hit a 200 address. He tries to come in, hits the router, and as we discussed in the algorithm of precedence, from out to in, we do NATing first, then routing. So we do NATing. The traffic gets NAT, the 200 gets NATed to 192.168.1, goes to the server. Still not a problem. But the problem is when the packet comes back in. So we have two replies, right? One reply was originally destined to 100, 100, 100. The other reply was originally destined to 200, 200, 200. But when the packet reached the server, it is on 192.168.1.100. So both the packets, the replies which are pending, have the same source IP address, 192.168.1.100, right? So it hits the router. Now the destination, we cannot do any routing for that particular destination because all we know, the second user could be coming from first cloud and the first user could be coming from second cloud. It is an internet IP address. So we cannot choose in which direction it lies. So there is nothing in routing that can help us out to push our traffic out from one interface, right? So what might happen is, because the router does not know it, and as we discussed, from in to out, we do routing first, then NATing. So in this case, our router, for the reply which has come out from 100, 100, right, which has come out on this interface, our router can actually route it out to this particular interface, right? And it can send the traffic on this particular interface and sends it out, right? So I'll just repeat again. Return traffic from the server, which was destined to a user which has tried to hit 100, 100, might actually be routed out through the other interface. So this is how the NATing on a Cisco router is configured. It does not maintain a state table which tells the ingress traffic so that it can reply and send the traffic out from the same interface. That is not maintained by a Cisco router. Okay. So to fix this issue, we have a little, let's say, workaround to fix this particular issue. What we do is we can assign two different IP addresses to the server on the same IP, like on a Cisco device you have secondary addresses. Most of the servers also let us assign different IP addresses on the same NIC, or you can add an additional NIC, right? Give them different IP addresses. Okay, so I gave an IP address, let's say 192.168.1.100 to one of the NICs, 192.168.1.101 to the other secondary IP address. Then when I'm NATing, I NAT one of the IP address to the IP address of the first ISP, the second IP address to the IP address of the second ISP. Alright, so this is my NAT statement. IP NAT inside, source static. So I am having two NAT statements, just like the last one, right? Here we have two NAT statements, it's similar to that. So if I want, I could have, instead of using TCP, I could have done a full IP NAT, it's the same thing. So the difference comes in, now we want to choose our routing. We want to push the traffic out through the correct interface, right? So we know that we are NATing 1.100 to the 100 IP address, so that we create a route map which pushes traffic coming from 1.100 to the 100 interface out, right? So we say if the traffic comes from this IP, hits the router, we use a PBR, push it out like this. If a traffic comes from this IP, hits the router, we use a PBR, push it like this. Right? That way, we will have the same traffic flow which we intend, and we will not run into the issues. Now, one interesting aspect of both of these scenarios is that it might work at times, right? Because even if the traffic gets NATed to this IP address and goes out like this, it might still work, right? The ISP will send the traffic out, but we will have asymmetric routing. Traffic comes in like this, but it goes out like this. And quite recently, most of the ISPs are implementing URPF, that is unicast reverse path forwarding check. So if a packet comes in and the source route does not point in the same interface, they drop it. So that means for this ISP, the reachability to this IP probably is like this. And if they receive that source IP packet on this interface, they will drop it. So you might observe an issue where it was working before, now it has stopped working. This could be one of the reasons. Alright, so yep, I'll go through the configuration once more. Same NATing, exactly what we had, right? But we are using now two different IP addresses. We use this is additional step that we have, a PBR, which we are using to send traffic out in the correct direction. So we'll go to a few more pitfalls. This time we will see them in the router, okay? So one is wrong network mask in the pool. Alright, so I'll just quickly pull up the router and show you that. Alright, so let me see what is here configured. Alright, so I'll remove the existing NAT configurations. Alright, so we'll start with this. Right now I don't have any configuration other than NAT. Alright, so now I'll create a new pool. IP NAT pool, and let's say I give it two IP addresses, right? 6.6.56.2 and 6.6.56.3. Alright, and I give a network mask because a lot of people are confused why the network mask is used, right? And they can use any mask, or they try to match the mask of the IP addresses that they have assigned. So here, let's say we mask it to /32. Prefix length, let's say /30 we make it, right? So our pool is ready. How do we check how our pool looks? Show IP NAT stats. So, okay, I'm not configured NAT yet, I just configured the pool, so I'll also configure NAT. Let me see any existing access list for this. Access 100 is good. So IP NAT inside, source list 100, pool, NAT pool. Right now I will show the issue only for a dynamic NAT, not for overload, because then I would need 65,000 traffic, more than 65,000 streams. Alright, so the pool is done. Show IP NAT stats. Statistics. Alright, so here this is a very important output. So here we can see right now I do not have any translations. Alright, so this is the old traffic that we had, and outside interfaces are these two, inside interface are these two. Alright, and we'll cover up these other outputs later on. Right now this is an interesting thing for us. Right, so we have this dynamic NAT with this mask. There's a starting IP, this is the ending IP, and number of IPs that we have is 2. Alright, so let's see what happens. I'll go to PC1 and I'll ping something on the internet. So I believe 89.89 is one of the IPs. Not working yet. Let me just quickly verify. .8. What did I think? Okay. .8. Right. I was able to ping it. Now, if I go to my WAN router, show IP NAT statistics. Right, I can see that one of the IPs from the pool is allocated, right? And if I do show IP NAT translation, I can see that my IP. So this is what Manas said. This is very important for us to understand these headers. Okay. So I came in from this inside local 1.1, and then I became this. This was my inside local. This became my inside global. This is what I became. I was going to this, and I eventually went out to this. Right? So whether that got translated or not. In our case, it is not getting translated. And we can see this entry is there. Now, you'll see this entry as well. It is called a half entry. What this signifies is, because I'm using this, you will see when you do a NAT without an overload, you put it on a pool, but don't do overload, or you do a static NAT. Right? This you'll see for a dynamic NAT, not overloaded, and a static NAT. What this means is, this IP address is, this global IP address is taken up by this private IP address, right? This local IP address gets this IP address, and because it is dynamic, it's going to stay there for some time. We'll quickly discuss or see how much that time is. And then for each flow, we get different IP address, right? So we'll see 192.168.1.1 is using for the ICMP, it is use one flow and other one as well, right? If I run this command again, it's gone because this ICMP translation has timed out, but the other one will still stay there, okay? If I want to see how much time will it stay, I'll just show it in a minute. But how many IP address we have in the pool? I'll quickly show it again. Show IP NAT stats. We have 2, right? Oops. IP NAT stat. We have 2 IP addresses, and I have used 1, so that means still 1 is available for me. So I go to this device and ping the same IP, 89.89.89.9, and I can't ping. And I'm getting a response. U is unreachable. So I wonder what that is and why we are getting it and who is sending it to us, right? So I do a debug IP ICMP. I send the same thing again with a repeat of 1. So let's see. I receive a host unreachable from 123.5. 123.5 is my WAN router, right? The one which is doing the NATing. Show IP interface brief, exclude and assign. It's him, right? So I go to PC2. He's saying host unreachable received from him for 10.1.123.2. Right? So 10.1.23.2 is me. Right? What has happened? So let's go to the WAN router. And this flow was supposed to be NATed, right? Because it is 10.1.1.23.2. If I click here, this is 123.1, this is 123.2, and I check my NAT statement. It's depending on access list 100, which has the full subnet. So it should have been NATed, right? See whether it got NATed or not. NAT translation, no, it did not get NATed. Statistics still shows me I have 1 allocated IP, but I still cannot NAT it. All right, let's see why. So I do a debug IP NAT on this. Let's do a detailed. All right, I go back to PC2, send a ping, go to WAN router, and here we can see cannot create a new entry, fail to allocate the address, right? So although we have an address in the pool, we are not able to allocate it. So why was that? I'll just show you now. Right, the prefix length that we used was a /30, and when we create a NAT when we create a dynamic NAT, the router does not assign an IP address from the broadcast or the network of that particular subnet. Okay, so if we talk about this particular subnet with a prefix length of 30, this means this network is 6.6.6.6.56.0, right? This is a network address with the first host being 6.6.56.1. This is the first host address. 6.6.56.2 is the maximum host address, and 6.6.56.3 is the broadcast address, right? So the second IP address that I took was a broadcast address. Why? Based on the prefix length 30. If I wouldn't have used prefix length 30 and would have used a /34, then this would have been a normal host address which could have been used, right? So let's quickly check. I'll quickly change my NAT statement just to have that as a /24, all right? So if I do this, I believe the router will not let me do this because the entries are in use. Let's quickly see it. Pool in use cannot delete, right? Because NAT translations are there, right? So I have to clear IP NAT translation. It goes off. No NAT translation. I'll try to clear the pool. It let me clear the pool. But this is not the right way. As Manas has already said, the right way to configure NAT is ACL, pool in any order, and then NAT inside, right? So if you remove it, it should be in the same way. First remove the NAT, then remove the pool. So what I did here is not correct. So I'll remove the pool as well. Alright, and now I'll create the same NAT statement with a prefix length of 24. Alright, and then I'll recreate the pool. And now do show IP NAT stat. Alright, so statistics, again, exactly the same thing it shows us, but there's a different net mask here. Alright, now let's see whether it actually helped us. I didn't change anything other than the prefix length, right, for the pool. I go here, send my ping, successful. I go here, send my ping, successful, right? And then I go to WAN router, show IP NAT translations. Voila, we got both the translations in. Alright, now one more very important command, as I told, is, let's say I had these two IPs, only two IPs in the pool, right? And now I have my third PC who wants to go to the internet, right? So he wants to do 89.89.89. As we know, he will not be able to go out because he's not getting NATed. I had only two IPs and both I have used. So when will he be able to do it? When will he be able to access the internet, right? So for that, very easy command, verbose on the NAT translation. It tells us how much time is left for each translation, right? So for ICMP, the default timeout is 60,000 milliseconds. That would be 1 minute, right? Time left is 12 seconds, right? And then the other ICMP, same way. And this is created because of the dynamic timeout, right? This timeout has actually 24 hours left. So each user will be, so even if the user goes home and is not accessing anything on the internet, the IP will stay with him for 24 hours. Now, I'll quickly show you how we can tweak these timers, right? So we have multiple timers in NAT, and I'll show you the commands through which we can tweak them, because this is not good. We don't have a user, we cannot give IP address to a user for the full 24 hours, right? So what I do is IP NAT translation timeout. Now, you can see a lot of things here, right? One is never, it never times out, and then another one in second. And we have a lot of other options. ARP timeout, DNS timeout, ICMP timeout, right? SYN timeout, TCP timeout. So we should know which timeout to use for when. If we are using dynamic translation, that means we are not using overload, then this is our friend, timeout, because we are assigning one IP address to one host, and then that host can use as many ports or whatever application from that IP address, right? So we don't care about that. So usually we set up this timeout. If we are using dynamic overload translation, the IPNAT dynamic, right? Then this will not be of much use to us. Then we are dependent on TCP timeouts, UDP timeouts, and ICMP timeouts. So ICMP is less, we should be okay with that. UDP is also less. Important one is TCP timeout. So let's see how much is the TCP timeout. All right, very easy. Let me see if I have a username here. I'll just configure a username. All right, before that, I'll just quickly show you what happens. I go here, I'll send some TCP traffic, okay? 89.89.89.8. Okay, it just got closed. Check my NAT translation. Verbose. Look at the TCP translation. Only 55 seconds are left. Alright. Now I'll change it a little. Now I'll show it again. I think I was too fast. So the time left for this TCP translation, that's how I know it's a TCP translation, right? Time left for this TCP translation is 55 seconds. Alright. Now I go here. Quickly configure a username Cisco, password Cisco, line VGUS 024, login, local. Alright, I do a login local, so I go back to my PC1 to the same telnet. Now I'm in, right? So sorry. No, wrong username. Cisco. Alright, I'm in. Now let's go back and see what happens over translation. Show IP NAT translation verbose. Now you'll see for the same TCP, time left is 1 hour. Sorry, 24 hours, whole day. Right? So here for the same TCP, the timeout was just 55 seconds, but here it is 24 hours. So here's how it works. When a NAT router receives the first in packet, the timeout is still less, right? It keeps probably at 1 minute or 5 minutes. I have to confirm that.
Hello? Sir.
Sorry for that. Alright, so for when it receives the SYN, the timeout is less. When it gets the full session, it creates a 24 hours timeout. Alright, how it can create an issue is, there's one more thing, I'll just quickly show it to you. Now I go to PC1 and exit out and quickly go to WAN router and check the timeout. So you can see which was left for 24 hours has immediately come down to 1 minute. This happens because the router sees the SYNAC FIN flags of the TCP translations. So if it sees a FIN or a reset flag, it quickly resets the timeout to 1 minute. Right? It will not eat up your entry in the NAT translation. But it might cause an issue if the TCP session is not cleanly closed. Right? Something happens, both client and server die at the same time, no one is sending a FIN. If those type of things happen, the timeout can stay for 24 hours. Right? So you might have an issue where your NAT is being used up because we are getting a lot of unclean closed sessions. Fix for that is very simple. IP NAT translation TCP timeout. I will set it to 5 minutes, I think would be good. So 300 seconds. I believe it is seconds. It is. I set it to 300 seconds. And I quickly go back here, do a telnet, go to the WAN router, do show IP translation verbose, and now you can see it has become 5 minutes. My TCP timeout has become 5 minutes. So this way I can control, but I will have to know what type of application I'm running. Does that application send keep alive? That TCP application sends periodic keep alive. So my this timeout should be a little more than that keep alive, right? Else I might see a lot of hung sessions. All right, so that was one session on this, and let me quickly pull up some more things. All right, so that was wrong network mask in the pool that we saw, already seen. The other pitfalls that we have on this is using permit IP any in NAT ACL. We should not use that. We should only permit the subnet from which the traffic is coming. We should not use log keyword in the ACL, which is used for NAT. Right? A simple reason for this is NAT flow is used in the Ceph path, but when you put a log entry in ACL, it is punted to the CPU. So it is not in the same path. So you can also see a lot of packet drops. If you actually want to log the sessions of the NAT, you can use NAT syslog services for iOS, and you can use a NetFlow export for an iOS XE. All right. And one final thing that we see is NAT exempt of VPN traffic. All right. So what happens in this is, let me quickly pull up topology and quickly show you what happens. Let's say I have this server, or let me go to a simpler diagram. Yeah, I have this server which I am NATing here, right? So that people come in and access my server, right? Now let's say on this cloud, I also have a VPN user. So the VPN user actually VPNs to my interface, right? To the same physical interface. Now, if that user tries, so what you will observe is in that scenario, that user will be able to access everything on the inside, but he will not be able to access this particular server. All right. The reason will be when he tries to hit in, right? The traffic will come in, hit the server, but when a reply goes out from the server, it will NAT it because of a NAT statement, and it will then go through a VPN tunnel. Because the VPN crypto is built on the same physical interface, the egress is the same, right? So the packet goes out and the PC gets it from the NATed IP. He has sent it to the private IP 192.168. He receives it from the public IP 100. So the session gets reset, right? A quick solution for that is when you're configuring your NAT statement here, you also put a route map where you deny in the ACL the traffic between the server and the private VPN pool. This concludes our session for NAT, and we will now continue with the basics of routing protocols. I'll just ask Manas to take over now. Thank you.
Okay. Hi. So I got a good coffee break and I'm back. Before I continue, I had a few people who were discussing in the question panel, and there was a slight amount of confusion about the inside local and inside global. So I just wanted to clarify that. Right. So I'm going to go back to that particular slide so that I can take a look at it one last time before we quickly get to routing protocols. All right. Just 1 second. So before the NAT scenarios, there it is. And like somebody correctly pointed out, there's a typo there. Okay, so that's another reason I wanted to make sure that, yes, Nidhi, exactly what I was talking about. So I'm going to fix that as well. So basically the packet comes in. Now the perspective, again, I'm going to repeat the 4 terminologies, right? Like I said a couple of times, this is a fairly important concept for you to, remember and know. So when the packet is on the inside, the IP address that it sees, right? Now I'm a user on the inside. My idea of the inside IP is 192.168.1.1. That's the inside local. As I pass the router, the inside local gets translated to the inside global, right? Which I have fixed now. So you'll see that now it's become IG or inside global, right? So inside local becomes the inside global as it passes the NAT. And from the outside world, the only IP that the outside world is seeing as far as the outside local and global is concerned is 100, 100, 100, 100, right? So it's basically the view from the inside and the view from the outside for the inside IP and the outside IP. So local, global, inside, outside. I'm hoping that makes it more clear. And yeah, I do agree that was inside global. I'm glad a lot of you caught that because it is written as inside global here. And when I was talking about it earlier, I did come back to it as inside global. But I think in that packet, outside local and outside global are the same, say somebody in the chat. Okay. Try and put your questions in the chat window just for the sake of time, but since that was brought up, I will tell you, yes, outside local and outside global would be same in this case because we are not changing the outside IP. I'm talking about the destination IP. So the packet's destination is 100, 100, 100, 100 in this case. So as it traverses the device, the only NAT statement you have is changing the inside IP, the source IP, from inside local to inside global. Hence, the outside global is the same as the outside local. It does not change at all. Okay. All right. Now I'm going to go to routing and continue because we were supposed to start with some routing today. Most of the routing that we would do, the hardcore part of it, would be in the next session. But let me just tell you briefly what we're planning to do in this session, right? So we want to take a look at EIGRP and OSPF. We see a lot of cases that come from different people on EIGRP and OSPF. So we want to look at things in detail next time. Here are the basics of some things that you need to be aware of and need to keep in mind as you're working with these 2 routing protocols, right? So if some of your questions that you might have in your mind are outside the purview of this particular presentation, I would recommend you to comment on this because this will come up on CSC, right? We'll take a look at that and try and streamline our next one to some of the concerns that you're facing in the routing protocol as we come up with the next session of the 25th. Right, so let me get started. So EIGRP, what are some of the things that you need to remember about this routing protocol, right? 1, it shares an update only when there is a change. Now that's important, and we'll visit it again in a later slide. But it's important to remember that it has triggered updates to neighbors, and it only updates. It sends out a packet only if there is some change in the topology or network. Right? Now, some of this is in comparison to old distance vector routing protocols. For example, the old distance vector routing protocols had to be enhanced to allow variable length subnet masking, right? Which is to allow subnetting in general. and EIGRP was designed with that in mind itself. It holds more information than the neighbors. It's again talking about the fact that it doesn't just just have information about the neighbor itself, but also some information about what the neighbor has about its neighbor, which makes it a little not completely distance vector, right? Summarize routes and do it anywhere. EIGRP allows you to do summarization at any point of the network, unlike some other routing protocols where there are restrictions. EIGRP uses RTP. Now, RTP, when some people hear it, immediately go to the voice RTP protocol. No, we're not talking about that. RTP is Reliable Transport Protocol. It is the underlying protocol on top of which EIGRP is running. So that is what makes sure that your packets are reliable for the reliable EIGRP packets. Then it has a complex metric. Now, the EIGRP metric can be as complex as you want it to be, depending on the different things that you can bring into the picture, right? So it's a fairly complex metric, and we will go into that at a later time. And it also prevents loops. Now, let's take a simple topology, right? R1, R2, R3, R4, and R5. We are running a little tight on time, so I'll try and cover as much as we can as far as what I was planning to do in this session is concerned. Two keywords that you need to understand very clearly as far as EIGRP is concerned. Everything depends on these two, right? The first is the successor. What is the successor in EIGRP? You have a successor as the best route to reach a certain network. So let us say, and I'm hoping you can see my mouse. Can you see my mouse? Can somebody just ping in the chat yes if you can see my mouse? No?
Yes.
Yes, okay, good. Perfect. So let us say that there's a network 100.100.100.100 in front of R3, right? So it gets learned via EIGRP through R5, R4, R2, and R1 finally gets it. Now, let us also assume that the best path for R1 to reach R3 is through R2. So the metric that R1 has to reach R3, that is R1 to R2 and R2 to R3, is called the successor, right? Because that's the best route that you have to reach that path. Now, what is a feasible successor? Feasible successor is the second path, right? It's not as good as a successor, but it's still a valid route. So, for example, R1 through R4, R5, and R3 probably can be a feasible successor. I say probably can be a feasible successor, but it looks like a redundant path. Why? Because there are two terminologies. Oh, some of my text is overlapping, but I'm hoping you can still read it. So the two distance values that you need to be aware of in EIGRP, the feasible distance and the reported distance. So I talked about feasible distance as the metric of the successor. So now the best path here is what? R1, R2, R3. So the metric of the successor is the metric that R1 has to reach the subnet behind R3. That's the feasible distance. Now what is reported distance? Reported distance is the metric from a neighbor. So R1 has a neighbor R4, right? Now R4 calculates its own metric to 100.100.100.100. So let's say R4 says that my metric to reach that particular subnet through R5 is a certain value. That value is the reported distance of R1 through R4. Do you understand? So the feasibility criteria, which effectively is simply something that says, can I make a particular path a feasible successor, is called RD less than FD, which is the reported distance, that is the distance of my neighbor to reach that particular network. If it is less than my own path to reach that neighbor, then I will accept that as a valid backup path. That's what it's basically saying. This is the feasibility criteria by which EIGRP gets that sub-second convergence, right? Because of the fact that it already has a feasible successor in place that it can fall back to. Okay, now we're going to look at a few things. I am not sure why this is getting cut off. I'm just going to stop the sharing and move this a little upwards because I do not want some of this to get cut off, right? Okay. So there, oops, that didn't help much, did it? In fact, I'm going to get rid of this. There. So there are three tables that you need to remember in EIGRP. The first is the simplest, the neighbor table, show IP EIGRP neighbor. You see the neighbor, which interfaces you're learning it from, and so on. The topology table, which is basically showing you the EIGRP's successors, feasible successors, all the information that it has gained by building the topology based on what it knows and what its neighbors know, right, like we discussed. And finally, the routing table. Now, EIGRP takes the best route that it has to reach a certain network and puts it on its routing table. Here's a little thing for you to remember. EIGRP does not forward its entire topology table to the peer. It forwards the best parts that it has to different networks to its peer. So that's something you need to remember about EIGRP. Now, let's step up a little further and then talk about the EIGRP hello package, right? I mean, or basically how neighbors are formed in EIGRP. So if in that diagram before where we were looking at R1 to R2, if we are to bring up EIGRP between R1 and R2, all we need to do is router EIGRP. What follows EIGRP is called the AS number. Drawing a parallel right now, what follows router OSPF is the process ID. Okay, so router EIGRP AS number, and then you specify the network, which in this case I've just assumed it to be 192.168 whatever 1.0/24. Okay, let's say that's what this is in this case. Now, remember, this is a very important thing, and that's true for EIGRP, for OSPF, for any internal routing protocol, right? The network command under the router EIGRP, router OSPF does not advertise that network. And this, unfortunately, is something that we see a lot of people seem to get confused over. The network command simply enables EIGRP on the interfaces which are covered by the network command. So if you do a 192.168.0.0 instead of what I've done there, it's going to enable EIGRP on all interfaces in the range of 192.168/16. It doesn't mean it'll advertise 192.168/16 as a subnet or as a network. Okay, and that's something important to remember as the basics of routing protocol in general. Now, what are the things that need to match for a EIGRP neighborship to come up? See, this is what happens when we transition slides through different tools. Just give me a second. I'm trying to get my slide up to a point where I can at least read it. Okay, I'm hoping you can see that because I'm not able to drag it upwards. So the three things that need to match for EIGRP neighborship to come up. One is the AS number. So two routers that need to be neighbors need to be in the same autonomous system. They need to have the same authentication, if configured, of course, but you don't want a random person to plug in their router into your network and be able to form a neighborship with your EIGRP peer. So you might want to configure authentication, but remember it needs to match on both sides. And the third thing is the K values. The K values basically are like a switch on, switch off switch, which is basically saying what I need to consider when I'm calculating the EIGRP metric. Okay, and that's the story for a different day. Let me continue. What are some of the merits of using EIGRP? It is highly scalable if properly designed. Now, you can see properly designed is in bold. I tried to bold it. It doesn't look as bold as I thought it was. But yeah, so it's highly scalable if properly designed. Because why? Because when you keep adding routers to EIGRP, it forms a neighborship, starts exchanging routes. Another router starts forming neighborship, starts exchanging routes, which brings us to the second point. It's simple to implement, right? And it also brings me to the point, it's a potential pitfall. Why? Because if you start connecting router after router in a chain, connect company after company in a chain, and start exchanging EIGRP routes, then you're going to run into problems. Because the simplicity of EIGRP often ends up in people creating extremely badly designed networks in the EIGRP world. So this is something we'll go into detail in the next session. I'm hoping some of you are looking forward to that. When we look at what would happen if we really create a badly designed routing protocol network, EIGRP and OSPF for that matter. Coming to the next point, EIGRP has very fast convergence because of the feasible successor, which basically means I already have in my table one path to get there and also a second path to get there, so I can converge faster, right, obviously. The third thing is talking about the dynamic multi-point VPN, right, which is the dynamic tunnel interfaces where you can create between multiple sites. Now, that's a very popular EIGRP deployment scenario. And it's very good in a DMVPN setup because one, it supports stubs. What does stubs do? It reduces the amount of updates that are being sent out by different spokes to the hub in a DMVPN setup. You can summarize anyway. That limits the number of networks that you're advertising out, limits the load on the cloud in general, right? And finally, it's a silent protocol. Only triggered updates. And I mentioned this in the first slide, but we're revisiting it because what that means is there's no periodic time when I start sending out updates in EIGRP. It's only triggered. It's only at a specific time. It's not that, oh, okay, I haven't sent out any updates for a while. Let me just send everything out again. EIGRP doesn't work like that. So it reduces the load on, traffic-sensitive networks like the DMVPN cloud, for instance. Now we step into OSPF, and I'm going to have Sumit come back on. Thanks.
Yeah, thanks guys. So I'll start with OSPF, and as we discussed, as Manas has already said, that this session is just an overview, and I think most of you already know what we are covering in EIGRP and OSPF. The next session that we'll have, we are having probably on 25th, will have a troubleshooting scenarios and the pitfalls like we covered in NAT. Okay, so I'll just quickly go through the OSPF part. It's an open standard. That means you can have a lot of vendors implement OSPF, right? I can run it with Juniper, I can run it with Checkpoint Firewall, I can run it with any other device. That is also changing with the EIGRP now. EIGRP is Cisco proprietary, but recently we have opened it up and other vendors can also implement it. So it's not open standard, but we have given up a draft where people can implement it, right? So it's not exactly same as OSPF being open standard, where a committee decides on what needs to be changed on. Other thing is, in OSPF, we have the entire view of the area, right? So when we talk about OSPF, one thing that you should keep in mind is OSPF, think OSPF in two terms. OSPF intra-area, right, within the same area, and OSPF talking to the other areas. These two things behave in altogether different ways, right? So most of the things of OSPF that we talk about, like having the entire view of the network, or we talk about sending the LSAs all the time, right? Or we talk about that we run SPF to get the best routes and all, right? Those things, and if there is a change, we run SPF. There's a change, we run SPF. Those things are different when we talk about the same area, and those things are different when we talk about a different area, right? I'll give a quick example. OSPF, when I say it has a view of the whole area, that means OSPF knows all the routers, all the links of that particular area, right? OSPF does not have entire view of the network. That means if there's a link or there's a network which is outside the area, that particular area routers will not know about it. They will not have the full knowledge about it like they have for the intra area. They will only know that through which router I am able to reach it, right? Sounds more like a distance vector routing protocol, sound more like an EIGRP, where I don't know where exactly he lies, I just know what is the best way to go to him. So that is it. Outside the area, it is like EIGRP or a distance vector protocol, but within the same area, I know everything. It is classless. And one more thing, a big difference when we implement OSPF, that we have to design it properly. EIGRP gives us a lot of flexibility. We can do a lot of stuff with that, and as we discussed, that is one of the pitfalls. If you do not do it with care, we can run into a lot of issues, but EIGRP will let us do whatever we want, right? OSPF is very strict. It will not let us summarize at any point. In EIGRP, I can summarize at any router at any interface, but in OSPF, I can only summarize at the ABRs or at the ASPRs. All right. So if I just want to restrict, like I'm using DMVPN and I have a hub and I have all the spokes, and I want to summarize the routes and send it to spokes, but if the link is ABR link, that is area 0 link between them, I will not be able to do it. Right? I can do it if the ABR link going toward the spokes is in a different area. Second is OSPF will periodically refresh the LSAs. So that is approximately 30 minutes. That means approximate because it can be more than that. We use a pacing interval where we collect a lot of LSAs and then refresh them in batches instead of just doing it at exactly 30 minutes. All right. So these LSAs will be refreshed. So in DMVPN environment, you will have the LSAs being exchanged. So if you have maybe a lot of routers, all the exchange will be the LSAs exchange will be going through the DMVPN cloud, right? And the other problem is OSPF recommendation is using maximum 50 devices in an area and having at max, I think 3 interfaces in different areas, right? Or 3 areas configured on a router. So these things do not usually scale well with DMVPN, where we also see up to 800 or thousands of spokes. Then we can actually scale OSPF, but we have to design it properly, right? We have to summarize it. We have to do a design before we go on to the implementation stage. And now quick working of OSPF. This is what you can use in any routing protocol. So this we will go into detail when we do the next session. And it is also applicable for BGP. It is also applicable for EIGRP. REP is a little different, but all three these protocols, it is applicable. First thing that you do is you detect the interface on which you want to activate that protocol, number one. Number two, you exchange packets on that, so you discover the topology, you discover your neighbors, right? So you build a neighbor table. Number three, so right now I'm talking about a generic protocol, but I will also then tell what it is called in the term of OSPF, right? So hello packets are sent, I discover my neighbor, I go into the two-way state. Then once that is done, I exchange LSAs with the neighbor, right? So in generic, it will be, I try to know what the other guy knows, and I try to teach him what I have, right? So this is a knowledge exchange that we do. So in OSPF terms, it is based on the LSA database exchange, right? So that we send across. We'll go into details in the next session. Then once this exchange is done, our OSPF database is populated. We get all the information that the neighbor has. We have given our information to the neighbor. We go into the full state of OSPF, right? And in EIGRP also we have exchanged the topology. And in BGP we have also exchanged the topology. Once that is done, then we run the routing. So all this thing goes into the routings database. BGP has its database, EIGRP has its topology table, OSPF has its database. So all that information goes into the database, right? And then we run that protocol specific algorithm. EIGRP will run dual, BGP will run its best path, and OSPF will run its SPF. So it runs it, it figures out what is the best route according to that routing protocol, and then it pushes it to the routing table, all right? Discover interfaces, form neighborship with the neighbor, exchange the routes, and run your algorithm and give it to the routing protocol. Same step for all routing protocols. And when we troubleshoot, we should know which part is broken so that we can troubleshoot it in that direction. Neighbor not coming up will be a different troubleshooting step, or we can start with, okay, route is not in the routing table. So we can start with all these 5 steps. Which one is missing, right? Do we have a neighborship with that guy who is supposed to teach us, right? Whether that neighborship is in full, right? Second is whether our databases have been properly exchanged. Whether I have the route in the database, and then is it in the routing table or not. So everything will have a different mode of troubleshooting. And once OSPF, everything is up, neighbors are there, everyone is happy, EIGRP would be silent, will be only sending hellos in a silent environment, right? But OSPF, as we discussed, will be periodically sending the LSAs. It will be flooding them out. Now, few more things in OSPF that we have to remember, and that at times causes problem for us, is OSPF has different type of areas, right? We have stub area, not so stubby area, and OSPF has different type of LSAs. If we have to understand OSPF, we have to understand how to troubleshoot OSPF. This is one thing we should really understand, and we will go in a lot more detail in the next session. What are the different LSAs? What information can I get from that LSA? What can I do with that LSA database that I see? Where do I see it, and how can I use to troubleshoot my network issue that I am having, or how can I use it to understand my network? One more thing, which is very, very important, and a lot of people get confused, is summary LSA is not summarization. All right? So in OSPF, you would have heard that then ABR sends a summary LSA, right? So this is also a very good interview question where we ask, okay, whether OSPF does auto summarization or not. And some people remember, okay, ABR and summary LSA, that is summarization, so probably it does auto summarization. But we have discussed OSPF is a classless routing protocol, right? So it will not do a auto summary. I don't even think there's a command under OSPF which would be like auto summary. So summary LSAs is the name of the LSA. So if you do not manually configure summarization on the ABR, it will be just taking the router LSA, taking those networks and converting them into summary LSAs and sending them out to the other areas. Okay, it will not manually summarize them. It will not automatically summarize them. You can do a manual summary if you want. Fourth is inter-area traffic passes through the ABR, right? So you might have 2 routers which are very close to each other, but which both of them are far from the ABR, both being in the different areas. The traffic between them will still go through the ABR. And the last one is all areas must connect to backbone. right? So this is where design of OSPF is very, very important. You have to design it properly, where all the other areas that you're having should connect to the backbone. And in case you get, let's say you have a chain, let me see if I can reuse the topology with Manas had. Alright, so let's say we have the chain of R4, R5, R3. Let's say all these routers are R1 is in area 0, right? R4 was the ABR for this area. And let's say R4 dies. So this R5 is cut off from the network, right? This R5 is cut off and cannot, if we have other networks behind here, R5, although it has a path through R2, but it will not be able to use that. Let us assume this is not an ABR, right? So you might have a physical path, but you will still be broken from the network. To fix that, the fix is try to fix R4, or a temporary fix could be using a virtual link between R5 and R1, which we'll cover later. But virtual link is a temporary workaround. You should not have a virtual link in a working setup because it makes things very complex for us to troubleshoot, and it is not a good design practice.
All right, everybody. Thanks for joining today. We've had a whole barrage of questions coming in over chat, and it was good to see all of the participation and interest from all of you. Feel free to continue adding questions on the post on CSC. Like I said, we will answer what we can, and the rest we'll try and address in the next session.